This is Chapter 8, Section 1. We're going to do our intro to chemical reactions now and also talk about balancing equations. I will go kind of quick through some of the first parts of this. It's for you to just write down the information that you see within the podcast, but we will get to the meat of this and I'll let you know where that comes in at. So, signs of a chemical reaction. You have evolution of heat and light. If you form a gas, most of the time if there's a color change, and back up on the third one, formation of a precipitate. A precipitate is formed when two liquids are put together and a solid is produced. So two liquids put together, a solid is produced, and that solid is called a precipitate. At the end of this chapter, we will perform multiple chemical reactions, and you will have to distinguish between the different signs of a chemical reaction. You will get to see all four of these take place, some of them multiple times. A brief refresher on the law of conservation of mass. The definition: mass cannot be created or destroyed in ordinary chemical reactions. That means the total mass has to stay the same for your reactants on the left and your products on the right. So in this example, to make water, we had 4 grams of hydrogen and 32 grams of oxygen. So our product mass would have to be 36 grams since we're not creating or destroying mass. If we looked at the number of atoms alone, atoms can be rearranged too in the formation. We start off with 4 hydrogen and 2 oxygen atoms. That will create 4 hydrogen and 2 oxygen atoms total within the water after it's been rearranged. As a reminder also, hydrogen and oxygen are diatomic elements. So hydrogen is in its diatomic state. So 2 hydrogens bonded together there, and you have 2 hydrogen molecules. Oxygen is in its diatomic state also. Again, reactants are on the left side of the arrow, products are on the right side of the arrow. You don't have to have 2 reactants and 2 products, but anything to the left, reactants, anything to the right of the arrow, products. A, B, C, and D are just generic. Some symbols that we're going to use within our equations, make sure you get these written down. Obviously, some of the most common ones are going to be those top 6 that you see there. The arrow means to produce or form. The plus means plus. It could mean react with. S, L, and G are the 3 main phases we have. AQ is aqueous, so that's something dissolved in water. And if you see a triangle above the arrow, that means you've added heat. Now, in writing equations, we're going to look at some of the descriptions and stuff that we have, but in writing your equations, things you need to consider. Identify the substances involved. We will use symbols to show coefficients, so that's highlighted there. My coefficients here are really 2, 1, which is understood, and 2. So those are my coefficients. We will show of what, so you identify those compounds. So that's hydrogen, oxygen, and water. And in what state, all of these are gases the way it's written. So again, remember your diatomic elements. There are 7 of these. So if you were to be given this example right here and you had to come up with an equation yourself, I'm underlining the important parts as far as the different substances. You still have to include how many of what and in what state. So writing that out, you do have 2 aluminum atoms. So Al, aluminum, the phase is not given, but that is in the solid phase at room temperature, which is, you'll go with the standard phase at room temperature if it's not given. Reacts with 3 copper 2 chloride. You have to cross over charges for the copper 2 chloride to get the formula, CuCl2. Aqueous is given, that's AQ. To produce, there is our arrow, and it is 3 atoms of copper. Again, phase isn't given, so you go with solid. And 2 aluminum chloride units. So aluminum chloride, again, ionic compound. You have to cross over charges. You get AlCl3 when you do that, and it's aqueous. We throw on the AQ. Now, other describing coefficients, again, if it's an individual element all by itself, individual atoms, we say atom. If it's a molecular compound that's covalently bonded, we use the word molecule. If it's an ionic compound, ionically bonded, we use the word unit. So in describing these right here, CO2 is 2 nonmetals, so it's got to be covalently bonded. So that is 3 molecules of carbon dioxide. 2Mg, that's a standalone element, so we use atoms, so 2 atoms of magnesium. And then MgO, that is an ionic compound. It's got a metal in there, so when you're going to name it, magnesium does not need Roman numerals since it's in group 2, so that is 4 units of magnesium oxide. Now we're going to get to the fun part here, and we're going to look at the steps for balancing our chemical reactions. And I'm going to give you 5 steps first, some other helpful tips, and then we'll go through an example. So you have to write the unbalanced equation first. In the example we just went over with writing equations, those numbers wouldn't have been given, your coefficients wouldn't have been given, but you could have used the words to come up with the proper formulas for your substances first, and then you would follow these steps to get your balanced equation. Step number 2, you're going to count your atoms on each side. So all the atoms of each element on the left side of the arrow and on the right side of the arrow, so for your reactants and your products. Then we will add coefficients to make our atom counts equal. And we do multiply. So it is the coefficient in front times the subscript behind the element to give you number of atoms. Step 4 is an only if necessary kind of thing. So what happens is sometimes people get through the 3rd step, they have balanced their reaction, and then at some point you've overbalanced. So if all of the coefficients can be reduced to a lower whole number, we will. If not, you did great first time around, and you will double check your work. Some other helpful tips before we get to our example. I highly suggest balance one element at a time. So once you add a coefficient, then recount your atoms. So add a coefficient and then recount your atoms. Do this after each coefficient. Please don't add 2 coefficients at one time, because you're like in your head that you think that you know where you're going, and then that is really common for mental mistakes to happen there. If an element appears more than once per side, you need to balance it last. I can tell you that the elements that are very common to appear more than once per side are oxygen, which is the most common. Balance oxygen last, and then hydrogen would be the one that is next to last. So these 2 elements, very common to them appear in multiple compounds on the reactant or product side, so try to balance those last. And then if you have a polyatomic ion that stays together, then leave it together. So if you have, let's say, barium sulfate on the left side and magnesium sulfate on the right side, then leave it as SO4 on both sides, and then we'll do our counts either way, and you will see some examples of this before it's over with. So let's go through our first example. We've got aluminum plus copper 2 chloride reacts to form copper and aluminum chloride. This example has left out all of our phases. So for right now, we're not going to add the phases, but I can tell you that the aluminum and copper are solid, and then the 2 chloride examples are both aqueous solution. But we're going to leave those out so we can concentrate on the balancing concept. So first thing you need to do is write your unbalanced equation, and that will look like this. Aluminum, which is not a diatomic element, so we write Al. Copper 2 chloride. Copper 2 chloride is ionic, so we have to work with charges. Copper is a +2, chloride is a -1. So when you take that and you cross over charges, you get, changing up my colors here, CuCl2 forms copper, Cu, and aluminum chloride. Same thing with aluminum chloride. It is ionic, so we have to work with the charges +3, -1. When you cross over those charges, you get AlCl3. In this example, we do not have any polyatomic ions, so that we don't have to worry about that. We're going to go ahead and go to step number 2, which is count our atoms on each side. I am dealing with, and I'm going to want you to show these atom counts just like what I am showing you right now. We have aluminum, we have copper, and we have chlorine. On the left side, which is our reactant side, we have 1 aluminum atom. On the right side, we have 1 aluminum atom. For copper, on the left, we have 1 atom, and on the right, we have 1 atom. And for chlorine, on the left, we have 2. On the right, we have 3. In step 3, we add coefficients. Coefficients go in these blanks to try and balance our atom numbers, and it is coefficient times subscript to get our atoms. The only thing out of balance right now is chlorine, and we are lower here on the reactant side, so that's the side we've got to bump up. We can only use whole numbers. In your head, I'm sure you're thinking, oh, some of you are like, yep, I'm going to go ahead and jump straight to a 3 because I know that's what I need. But we do start off low just in case, because sometimes when you skip coefficients from 1 and you skip over 2, then you've actually skipped over the correct answer. And that'll be entirely true if we were dealing with, say, hydrogen or oxygen that appears more than once per side. Start off low. So I am going to put a 2 here in front of copper. So now that is, I'm focused on copper. 2 times 1 is 2. 2 times 2 is 4 for our chlorine. So that 2 out front, your coefficient, does change both of the elements that are behind it. And if I go to the other side, copper is out of whack and chlorine is still out of whack. So I'm going to go ahead. I can do either one at this point. I'm going to focus on chlorine again. Try to get chlorine bumped up to 4, but any number you put in front of AlCl3 is not going to give you 4 chlorines. But I will start with the lowest value. And the lowest value that we have now is still a 2. So that changes aluminum to 2, and it changes chlorine to 6. So again, everything's out of balance. I'm still going to focus on chlorine, because if I look back at chlorine right now on the reactant side, this left side, there is a number I can put in front. I can change that value to something that will give me 6 chlorines. So if I go back in at this point and I change that to a 3. Copper now has 3, and chlorine has 6. Yay, chlorine is balanced. We are good to go. We can focus on copper and aluminum. Copper, on the right side, I will put a 3 in front of copper. That will give me 3 copper atoms. For aluminum, on the left side, on the reactant side, if I put a 2 in front of aluminum, that gives me 2 aluminum atoms. And it appears that my atom counts are now equal on each side. My coefficients are 2, 3, 3, and 2. Those cannot all be reduced to a lower whole number, so I've double-checked my work. I am good to go. Let's do one more example. So in this example, I'm going to tell you the name of the compounds, but I'm going to go ahead and write them down. We've got sodium hydroxide, that's ionic, if I cross over charges, plus sulfuric acid, yields sodium sulfate. And before this chapter is over, you're going to learn how these reactions take place, and you're going to be able to predict products on your own. And water. So we're going to go through and balance this reaction. Now, in the helpful tips I gave you, it said balance one at a time, but if you had any polyatomic ions, if they stay intact, leave them intact. So I notice there is sulfate. SO4 is still SO4 on the product side. So I will leave that as SO4 and I put parentheses around it. I don't want me to do anything with that little 4 that shouldn't happen. I see another polyatomic ion, which is OH, hydroxide, but on the product side, it is not still hydroxide. So for that one, I will have to break the O and H apart and treat them individually. So I will go and take parentheses off of it. So starting back again, we have our unbalanced equation. Step 2, our atom counts. Let's go back and identify everything that we need. So we do have sodium, we have oxygen, we have hydrogen, and then that sulfate that I had pointed out. So sodium, on the left side, we have 1 atom of sodium. On the right, we have 2 atoms of sodium. Oxygen, on the left, and I'm going to show you where I'm getting these numbers. I see 1 oxygen here, but this sulfate oxygen is taken care of in sulfate, so I do not add it. So oxygen, there is going to be 1 oxygen on the left. On the right, again, I'm not going to count those oxygens because they're in sulfate, but I will count this oxygen, which there is 1. Sulfates. Well, on the left, I have 1 sulfate unit, so I put a 1 out front. And on the right, I also have 1 sulfate unit. Hydrogen on the left. Now this is where it gets a little tricky. I have to account for that hydrogen and these 2. So it is 1 plus 2 gives me 3 hydrogens. On the right side, hydrogen is only right over here, and there are 2 atoms of it. So I do have 2 hydrogen atoms over there. So notice hydrogen is in multiple places on the reactant side, so I will want to wait till the end to balance it if possible. So as I look at my atom counts, the only thing out of balance at this particular point are the sodium and the hydrogen. So I want to start with sodium. It's not that that is the only way you can do it, it's just to make it a little bit easier. On the left, sodium is too low, so I will add a coefficient on the left to bump up sodium. That does give me 2 sodium atoms. It also, on the entire left, gives me 2 oxygen atoms because I don't double count oxygen and sulfate. But it gives me 2 hydrogens here, and I still have 2 hydrogens there, so 2 plus 2 is 4. So it gives me 4 hydrogen atoms to work with. Now, the only thing out of balance is the hydrogen. On the right side, we are trying to bump it up. Well, I want to get it to match this 4. So if I put a 2 in front of water, that does give me 4 hydrogens, but now it changed. Oh, I didn't notice it. Oxygen's out of balance too, but that gives me 2 oxygens. And if I look at my final results, 2, 2, 1, and 4, 2, 2, 1, and 4. Looks like everything is balanced. So my final coefficients of 2, 1, 1, 2 balances out this reaction. It is ready to go. Those cannot be reduced. Final answer.